that your probability changes, right? The second time you go in is not the same as the first time, 3 out of 30. Now you only have 2 out of 20 out of 29. Everybody see this item here?
Yes, sir.
Then
So-
would that be considered dependent?
Yes.
Okay.
Not independent, so it's dependent. Yes, they depend on one another, and that's why it's dependent.
So when it's dependent, basically the denominator are two different numbers.
Right.
You have to do a replacement because it's without replacement. Okay.
Right. And that's where, that's where remember the example in the first, when we start out and I told you guys about the computer, the defective computer, they did not spell it out in terms of without replacement. They just say, okay, the first event, you go and you select a defective one, which is 3 out of 10. The second one, you go in, given that you take out A already, right? You take out A, meaning you take out one computer, you go back, which is everybody see that you don't replace the first computer back. So that's why they are dependent or they are not independent. Okay, so is this a little bit, easier to understand about dependent versus independent?
Yes.
Yes.
In the sense that if you don't replace it, if they affect, if they affect them, then they are. If there are some effect between the thing that you do, then it's dependent. If there's no effects, which is the probability is the same. Like you flip the coin 10 times, you get the same. The probability of flipping the coin is the same. 1/2, 1/2, 1/2. They are independent. Okay. So again, that's one thing to look at is does your probability change it? Okay. And I will, so question with this item here. Let's attack another problem with again, if you divide this, you have 0.007. And again, let's attack this problem here. Let me erase this. So let's attack this problem, right? This is the problem that we haven't done. And again, your homework probably looks something like this, right? So let's take a look at this thing here. Example, target practice. So again, I just take this problem in your book. So most maybe you probably have this question on your homework. But again, they say Laura and Philip each shoot one shot at the target. Laura have the probability of 0.5 of hitting the target, and Philip have a probability of 0.3. So let me ask you guys, right here, they say that the shot are independent, but everybody see why that they are independent. Because Laura and Philip are different people, right? Which is again, Laura probability is different from Philip probability. Agree?
Yes.
And again, if they say Laura shoot the first shot and then Laura shoot the second shot, then now they are kind of dependent. But this one here, Philip is different from Laura. So again, the two shots are independent, right? And if we figure out, because they spell it out for us, they say that the shots are independent. Now they ask you find the probability that both of them hit the target. So again, if they are independent, all we need to do is find the probability of Laura hit the target, multiply to the probability of Philip hit the target. And again, do we have that? Do you agree that they give us that? They give us that the probability of Laura hit the target is 0.5, and the probability of Philip hit the target is 0.3, which is those are the probability that they give us, right? And again, they don't have the chart. They just give us the probability. So if we know that they are independent, all we need to do is take the first probability, multiply to the second probability, which is everybody see the probability of Laura hit the target is 0.5, multiply to probability of Philip hit the target, which is 0.3, which is if you multiply them, you get 0.15, which is again, the probability of both of them hit the target is 0.15, right? Laura shoot first, Philip come back, shoot a second time, and both of them hit the target is 0.15. Okay, so again, they spell it out for us, which is they give us everything we needed. They give us the probability of each individual one, and then they give us they ask us what is the probability of both of them hit the target, which is we know that probability of Laura hit the target and Philip hit the target is multiply the two probabilities together. Okay. Now, the second one, given meaning, as you can see, there is a conditional probability. Given Laura hit the target, the probability is 0.05 that Philip hit the target closer to the bullseye than Laura. So again, the condition here is Laura had to hit the target, and then Philip will hit the bullseye closer than Laura is 0.1. Okay, meaning again, looking at this thing here, if you dissect this again, the probability of Laura hit the target is the same, which is 0.5. It does not change. But again, this is what they give you is the probability of Philip hit the target closer to the bullseye, given that Laura hit the target already, which is everybody see that this is a conditional probability that Philip hit the target given Laura hit the target first. Okay, so again, given, which is again, they give you this probability here, which is a conditional probability. Now they ask you find the probability Laura hit the target and that Philip hit this target closer to the bullseye. So looking at this thing here, because of this conditional probability, everybody see that this is dependent, right? First, Philip have to depend on first Laura hit the target. If Laura didn't hit the target, we don't know. Right, this one here is depend on that, which is again, as you can see, the probability change it, right? The probability change it is no longer 0.3. Last time individually, Philip is 0.3, but this time they give us some condition, they give us some other probability, which is different, which is in this case, again, to be in short, this is all we have is we just take the two items and we multiply them, right? We just take the two items and we multiply them. It's just that now this one here, because they give you some condition, and the condition is, again, Laura hit first and Philip hit closer is 0.1, which is, that's the probability, which is, again, no, in short, you just take the two probability and multiply. But to compare A and B, A, they are independent. B, they are dependent because the probability change it, okay? Because the probability change it, that's why they are dependent. Okay, in that nature, if you want to attack dependent versus independent. Okay, but again, but B, because it's a conditional probability, that's why we using the probability, not the 0.3 anymore, because there are some conditions met. So we using the 0.1. Okay, but again, the math. One thing like I mentioned is the math is hopefully you guys see that the arithmetic is very easy, right? The arithmetic is just multiply fraction, add fraction, subtract, divide, right? But you know, how do we get to this point? That's the challenge, right? But anyway, question with A and B here. Right.
I'm sorry, you said that B is dependent because Philip depends on Laura hitting her target first, right?
Right.
To see if it, okay.
Right. So let me, I have probably 8 minutes or 6 minutes. Let me show you, let me give you a different sharing. Give me 1 second here. Let me new share. Let's take a look at this thing here. Let's take a look at this thing here. Well, let's attack the at least one, and then let's attack the at least one portion, and then we will continue with this tomorrow. So again, looking at this thing here, they ask you to solve the at least once. So this is the last thing in 4.3. 4.3. This is the last item is, what is the probability? This is what they ask you is a fair coin, which is 50-50, right? Toss 3 times. What is the probability that it's come up tail at least 1 time? So again, it doesn't matter if it's come out tail first or come out tail second or come out tail third. As long as it come out at least 1 tail, then it's in this probability of at least 1. Everybody see that? So let's take a look at this thing here. This is the sample space. This is the sample space for tossing a coin 3 times. Okay. So the first time, if I toss the coin, do you agree that if I flip the coin here, the first time I will either have a head or a tail, right? The first time I flip the coin, I either have a head or a tail. That's 50-50, right? So now, let's say if the first time I toss a coin and a coin come out a head. Do you agree that if I toss the second time, I will either have a head or a tail, right? And again, if I do the third time, everybody see that again. Meaning, looking at this thing here, the first toss, the first flipping, I have head. The second I have head, the third time I have head. Which is, if you look at this thing here, my sample space is I can either have a head, a head, a head, a head, a head, a tail, right? First head, second head, third one tail. Or I can have a head, a tail, and a head, and a head, a tail, and a tail. Everybody agree that, again, those are my first item is a head. Vice versa, for the tail, I can either have a head, tail, and basically everybody see that this is my sample space here. My sample space is, I have 8 different sample space. What are my 8 different sample space? My 8 different sample spaces, I can have either all 3 of them head, 2 head, 1 tail, 1 head, 1 tail, 1 head, which is, it's again same 2 head, 1 tail, just different order, right? Different time it's come out, right? A head, 2 tail, a tail, 2 head, and vice versa, 3 tail as the end. So looking at this thing here, everybody see that this is my sample space. If I flip the coin 3 times, this is every possible combination of head and tail can come out. Okay. First of all, everybody see this sample space here.
Yes.
Now, what is this? What is this at least one? Everybody see at least one mean as long as I have 1 tail. This is at least 1 tail, right? Doesn't matter when the tail come out. As long as I have 1 tail, that means at least 1. Do you agree that this one is have at least 1? This one have at least 1, even though they have 2, but they have at least 1. Remember, at least 1 is the minimum, go all the way to the maximum, right? At least 1, right? And again, at least 1, at least 1, at least 1, at least 1. So everybody see right here, at least 1, meaning I have this. So what fit the description of at least 1? Well, the description of at least 1, if you look at this sample space, easy enough. How many items have at least 1 tail in it? Which is, everybody see that I have 7 items over 8 possible outcome. Which is, again, the probability of me flip the coin 3 times and I have at least 1 tail. Doesn't matter when the tail come out. As long as I have 1 tail, that's at least 1, which is I have 7 out of 8. Everybody see that? So you say, oh, that's easy enough, Mr. Tran. If I know the sample space, then I can look at this and then I can see that 7 of them contain a tail, right? And 1 of them does not contain a tail at all, right? But the reason why I picked this because the sample space is small, it's only 8. What happened if I swip the, what happened if I change a script a little bit, right? What happened if I want to toss this coin? I want to flip this coin 10 times, right? And if you want to, flip the coin 10 times, as you can see, the outcome of this thing here, or the sample space, will be humongously big. Why humongously big? Because it's basically 2 raised to the 10 power. As you can see, this right here, 2 raised to the 3 power. We flip 3 times. 2 raised to the 3 power, 2 times 2 times 2. That's why I have 8 sample space, right? This one here, 2 raised to the 10 power, that's 10,000. I'm not 10,000, sorry, 1,024 different sample space. It will take forever to construct this tree diagram. So looking at this thing here, if we were to have this thing here, ladies and gentlemen, this is the at least 1. The formula for at least 1 is this. The formula for at least 1 is the probability for at least 1 is 1, which is your maximum probability minus the probability of none. What does it mean? The probability of none? Do you agree? Do you agree that the worst case scenario is I have none. I flip 3 times, none of the time come out a tail. Or I flip 10 times, none of the time come out a tail. right? So probability of none, meaning that's the worst case scenario because I need at least one. Everybody see right here, this is the none part. None of the time, the head, none of the time I have a tail, right? So if you want to, the probability of at least one is probably is equal to the maximum probability, which is 1, minus the probability of none, which is if we were to attack that problem before, I just take 1 minus again. Do you agree that none of the time have a tail, which is 1 out of 8, which is again 8 over 8 is one whole number, which is 8 minus 1 will give me 7, which is everybody see that it's the same result, 7 over 8. And again, if you were to want to answer the bottom here, one term that doesn't have any tail will be head 10 times, right? If you flip the coin 10 times, and the probability of none of the time come out of tail is you have one of them. Everything else have at least one tail. So to find the complement of that, we just take 1 minus that, which is again the probability of this item here is pretty much 1023 over 1024, and whatever that probability is, at least one tail. Okay. But again, the reason why I use this thing here is hopefully you guys can see that we can construct a sample space, and looking at the sample space, we can see that there are one term that doesn't come out the tail, right? But the problem that you will see is something like this, and we will pick up on this problem tomorrow. Okay, and again, the probability of at least one, which is you take the maximum minus the probability of none of the time that is come out, or in this case, none of the time chap will win the ticket or the lottery. Okay, so we will begin with this tomorrow, which is begin with 4.2 tomorrow, 4.3. Finish this at least one. Hopefully tomorrow you guys can see it, and then have a little bit better understanding of the at least one. Question here. Question with this particular item here, which is the tail item, the head or tail item.
Yes, I was a little confused on where it says equal 8 over 8.
Right. A over A is basically, again, in order for you to subtract fraction, you need to have a same denominator. 8 over 8 is one whole number. It's pretty much, instead of say 1 is 8 over 8 because A going to A is one term. So right. 8 over 8 is one whole number, and then you just take 8 minus 1 to give you 7. And you kept the denominator. Right. So again, you can use your calculator and take 1 minus 1 over 8, and your calculator should give you 0.875 anyway. So I just wrote a arithmetic here. Is 8 over 8 is one whole. So
right. Okay.
That's all.